right, let's get started. Let's do this. Today we're talking about BSTs. And my stress level's already going down. The last lecture I had 10 minutes of technical difficulties with the friggin' podium in the room. All right, this one's going smoother already, but hopefully it keeps going that way. So last time we talked about binary trees, and we built the binary tree node class, and we saw our three traversals just to get used to the structure of a binary tree. Now let's see an application of that, because one thing that was very notably missing from Monday's lecture was, why the hell would we even use this thing? Why would we ever use a binary tree? So let's answer that. We're going to see one application of binary trees in binary search trees. This is something we can build with that binary tree structure, and without it, we really can't. I mean, it's got tree in the name. So we're going to talk about what it is, and then at the end of the lecture, we'll finally get to why the hell we'd want to do this. So binary tree, a binary search tree, is a tree where, and I'm going to shortcut. I shouldn't do this because it always is a little bit confusing. Oh, and since I had so many difficulties, I never got in big mouse mode. Oh, man. I had to lecture from the classroom computer, and it sucked. So a binary search tree is a binary tree that we're going to give a comparator to. We're going to give it a comparator, and then for every single node, we have two properties that have to hold. Everything to the left of that node, all of the values in its left subtree have to come before that node in fully sorted order according to the comparator, and everything to the right has to come after that node in fully sorted order. So for this one, I'm using the standard less than comparator for integers, which my examples will use the less than, but this can be any comparator ever. We might be sorting game items based on their distance to a player. It could be anything that we're sorting. I'm going to use the simplest one, counting numbers up. Like, that's the simplest one that we're all familiar with. I'll use that for an example, but we can use any comparator ever for these things and any type ever for our nodes. Everything's completely generic. But if I say less than, just because I don't feel like comes before according to the comparator, I'll start saying less than, but that could be in place of, that's just in place of comes before according to the comparator. I just don't want to say that many syllables. Okay, so for the root node, everything to the left is going to come before 5 in this case, which we can verify is true. Everything to the right comes after, and that property has to hold for every single node. So for this node, the same thing is true. 2, everything to the left has to be less than 2. Everything to the right is greater than 2. 8, everything to the left is less than 8. Everything to the right is greater than 8. If these two properties hold for every single node in the tree, we have ourselves a binary search tree. So these are the properties of a binary search tree. And then one question has to at least be thought about is, how do we handle duplicates? So if we have a tie, we ask the comparator, and it says these two values are a tie. For our example here, if I want to insert 5 into this tree, we have to break ties in some way. We just have to decide how that's going to happen. For some trees, and depending on your application, you're going to choose one of the three options of how to break ties. 1, break ties to the left. 2, break ties to the right. And 3, don't allow ties at all. If you try to insert a duplicate value, just don't insert it. If we try to insert 5 into this and we see that 5's at the root, or 8, we go down here and see that 8's right here, we just say, never mind, it's already in there, don't allow duplicates. Which is a really handy thing to do if our application is building, say, a set. We want to build a set that doesn't allow duplicates, we just don't allow duplicates. If we do want to allow duplicates, we want to preserve every value that's added. We decide either left or right, and as long as we're consistent, it's not going to break our algorithms. But that's a binary search tree. And the example I used on Monday just happened to be a binary search tree, so we could get used to seeing this structure, this everything to the left is less, everything to the right is greater than. Oh, I didn't say anything about that. We have 116 in the middle of the eclipse. I won't be here on that day. There won't be a lecture question. Attendance will be optional. But Paul and I are still talking about what exactly to do. We might just cancel it outright. We might do a video lecture. But April 8th, there won't be a required lecture that day. Go out and enjoy the eclipse. That'll be Eclipse Day. I think the university should just cancel it. My kid's school is canceled. They just canceled school for that day. I don't know why we can't do the same. So plan accordingly. Once Paul and I come to a decision, we'll update the schedule and make a more official announcement. All right. I know it's exciting. Settle down. All right, so we have a BST. That's the properties that we have to have. So let's code this thing up. And here's our basic structure of a BST. Similar to the song class, there's some parallels to that in that it has a reference to node-based data structure. Our song class had an instance variable that was a reference to the head of a linked list. Here we're going to have a binary search tree class that has a reference to the root of a binary tree as a binary tree node. So kind of the same idea there, except we also have to have a comparator. All of our comparisons are made based on a comparator, which we're going to take in the constructor. The constructor is going to specify the comparator. We're going to initialize the root to null, which it is by default already initialized to null by being explicit. So we're going to set equal to null, or we could put equals null up here. Either way, that's initially null. So we have all of our null-based checks like we had for linked lists. We're going to check for null. If it's null, that means the tree is empty. So if the tree is empty, we're going to want to do one thing, and if it's not empty, we're going to do another thing. We're always going to start with that conditional. If root is null, do this, else do that. So make sure we have all those checks. We should be used to that after task 3. Same thing is going to apply for task 5. Jesse, dipping for the eclipse? Yes, I'm dipping for the eclipse. It's a rare. I always want to say once in a lifetime, but it's not once in a lifetime, but it's a pretty damn rare event. Like, go out there and enjoy it. Get the glasses and everything so you don't burn your eyes and stuff, but go out there and enjoy it. There are people traveling across the country to come here to see that eclipse. I think we can travel outside to see it. So for BSTs, we have 2 methods that we want to write, insert and find. These are the 2 that we're going to write to handle basically what we want to do with this thing. Insert and find. Insert to add values into the BST and insert them in a specific location that's not going to break the property of a BST. And find, how can we find a specific value? And this one is going to return Boolean. Our find for linked list returned a reference to the node. We're just going to return a Boolean this time, keep it a little simpler. Not much simpler, but a little bit simpler. And this is how we'll use a BST. This is how we'll call the methods. We'll create a brand new BST, call that constructor that takes a comparator matching the type of the BST. So if you have, say, a BST of songs that you need to keep songs in sorted order, you do a BST of song, create a new BST, and then new song title comparator, song Bayesian average comparator, whichever one you want to use for your testing. That would be the setup. For the homework, since I kind of mentioned it already, I'm in too deep now, I got to talk about it. The BST class, it's not in the handout, and nowhere in task 5 does it say you have to use a BST, but that is the expected answer. That's the expected solution. At some points, you have to return a root to the tree that is in the structure of a BST, but nowhere does it say you have to use the BST stuff that we're talking about in lecture. Like, you could build your own, but don't. Any code that we give in lecture or anything that's in the examples repo, that's fair game for you to use on your homework. So the BST code that we're going to go through, just take that BST class paste it into your project, preferably in the data structures package, and then use that code verbatim. Don't try to do anything too fancy. Just use that and then call it like this, but with song and one of your song comparators right here. And then insert anything you want to insert. Find anything you want to find. And in-order traversal, we're going to see, is a very important thing. I'll save it for a later slide. But in-order traversal is going to be an important thing to use for BSTs. And I'm going to use the less than comparator. So this will sort our integers in increasing order. And we expect all of these nodes to be inserted into the tree and maintain that property. So our insert method needs to maintain the property of everything to the left is less than, everything to the right is greater than. And I'm just going to avoid ties for my examples. My code is going to have to handle ties, and I'll break ties arbitrarily. I forget if I chose left or right. I think right. But it's going to have to maintain the property of a BST. And here's insert. There it is. There's all the code. We'll go through it step by step. But I have an insert method. It takes a value and returns void, and I have to maintain that property. Now, initially, my tree is empty, so root is null, and I have to check for null. That's the first thing I'm going to do. If root is null, well, root is now a tree with one value. The root is just a node with null, null as its left and right, and the first value that was inserted. So right from the first value that's inserted, the property holds. There's only one node. It has no left or right child, so the property holds. It is a BST. And then after that, we have to be careful when we call our insert helper here. When we get into this, we have to be careful to maintain that property. So that's what we want to do, maintain the property. Everything to the left, less. Everything to the right, greater. So once the root is not null, now if the root's null, if I ever get into this block and I say this dot root dot, null pointer exception right there. We can't use the dot operator on null. We're going to get a null pointer exception every single time. We don't want to do that. But if we ever get into the else, since our condition was if root equals null, if we're ever in the else, we know that root is not null. It is a BST node. It is, or not a BST node, but a binary tree node. We know that it's a node, so we can treat it as not null. So we're going to go to insert helper. We want to start some recursion with trees. The recursion is going to pay off significantly. Like I said in the last lecture, writing any tree algorithms with loops, not any, but a lot of these tree algorithms with loops is pretty tough. Actually, this is one that you could get away with a loop. But your tree traversals especially, not going to be so easy. So we want to get used to recursion here. So we want to start off the recursion, but this method only takes a value, which is going to be tough to work with the recursion. The recursion needs to keep track of all of the information it needs to do what it needs to do, and in this case, it needs to know which node it's currently visiting. Now, for our first linked list algorithms, we used this dot to be able to know which node we were visiting because all our code was in the linked list node class. But that's not the case here. We're in the BST class, just like when we're in the song class, we can't do that same trick. Just like the list of doubles class, we couldn't do that same trick. We can't do that here. So we're going to create a helper method that takes the values that we want, the node that we're currently visiting, and remember the value that we're inserting. Because the only way we can pass knowledge from one stack frame to another is through the parameters, the parameter list. And for methods, we have the keyword this also. But this is always a reference to the BST itself, which just isn't helpful in this situation. So we're going to pass information through the parameters. So the node and the value to insert both have to be parameters of our helper method. And then we'll start off our helper method at the root and then insert that value that's being inserted. That value is just going to be passed on from call to call. The helper is going to do the actual recursion of figuring out where to insert this value. And it's going to do that with the comparator. That's the only thing we have to be able to tell the order, the actual order that these things should go in. Where our comparator for our example was less than, but our code has to work with any comparator of any type. So we're going to call our comparator and ask it what it thinks. So we call the comparator. This is a reference to the BST. Comparator.compare is the method that we override to decide how to compare. So we're asking our comparator, does toInsert come before the node, the value at this node? So we're comparing those two values to decide whether to go left or right. We're saying if toInsert comes before this node's value, or in our int example, is the value I'm inserting less than this node's value? If that's the case, I need to be thinking left. I need to go to the left to figure out where to put this thing. And if I look to the left of this node and I find null, I found a home for the value that I'm inserting. If I say, okay, the comparator says go left. Comparator says go left, I look left, I find null. There's an open spot in the tree right here. I'm going to put this node right here. I'm going to use my setters this time. We're not in the binary tree node class anymore, so I can't get away with .right, .left like I was last time. We're going to call set left and set left to a new binary tree node with that value and null, children. If I look to the left and it's not null, recursion. We're going to move on to the left child through recursion. We're going to move to the left by making a recursive call that has the left child as a parameter. So we're going to move to that to the left, because now on the new stack frame, insert helper gets a reference to this left child and starts the process over. Checks, do I go left or right? If I'm going left, is that space available? If so, insert it and end the recursion. Otherwise, continue recursively going down this tree until I find a valid spot that is null, and that's where I'm going to insert. If the comparator returns false, I'm going to go right. So my ties are being broken arbitrarily to the right. As long as I'm consistent, that's fine, but I'm going to choose right for this. If that comparator returns false, whether it's a tie or this node's value comes strictly after the value that I'm inserting, in either case, I'm going to the right. So I'm heading to the right, and if I look to the right and I find nothing, well, I just found a home for this value that I'm trying to insert. Otherwise, recursion, just move on to the right and keep going down the tree until I find a home for this value. So the way we're using this comparator, we're always checking the comparator to see which way to go, and the way we're using it is going to maintain that property of everything to the left is less, everything to the right is greater than, because if it's less, we're going to the left. If it's greater than, we're going to the right, and then we're breaking ties to the right as well. But we're always checking that property and making sure it's maintained as we're inserting into this tree. So for visual on that, we have this tree and we want to insert 7. We're going to ask our question, does 7 come before 5? In our case here, is 7 less than 5? That's going to return false, so we're going to move right. So our comparator returned false. We get into our else. We're going to look right. We see that right is not null, so we're going to make a recursive call, a new stack frame with this node as an input, as an argument. And then the recursive call, the next stack frame, is going to have this node as a reference and still trying to insert 7. And it's going to ask, does 7 come before 8? In our example, is 7 less than 8? That's going to be true. So we're going to think left. We're going to look left of this node. We're going to find null, which means we found a home for 7. And that's where we'll insert 7 based on this tree in our algorithm. Oh, thanks for the reminder, Zaid. Yeah, there's bi-weekly review session. Wait, didn't we change it to Zaid? Zaid, you're not in here, are you? Isn't review weekly now? Review, oh, that's a question for Zaid. Yeah, I think review session's weekly now. I thought Zaid agreed to do weekly. But anyway, review session tomorrow. It should still be a pinned post on Piazza to get the location details, time and location and everything. I think it's NSC 210. I remembered last time, but I forgot now. 210 at like 5 or some, I don't know. Check Piazza. I'm pretty sure we made it weekly. I booked the rooms for him to make it weekly. Okay, he must have just been in the habit of saying bi-weekly. This should be weekly now. Not next week, though, for obvious reasons. And if we want to, I think I only have one example here. Then all the stack frames return. But I want to go through another one if we want to, just to make sure that we're clear on how this happens. If we want to insert, say, 3 into this tree, we're going to ask, is 3 less than 5? True, go left. Is 3 less than 2? True, or sorry, false. I can do this. False, go right. Is 3 less than 4? True, go left. We find a home, and we would insert 3 right here. If we did want to insert a tie, we're breaking ties to the right. So say that I wanted to add 8 into this tree. Is 8 less than 5? False. We go this way. Is 8 less than 8? False, because we're using strictly less than. So it just naturally goes to the right. That's how we're breaking our ties to the right. Is 8 less than 14? True, go left, and we would insert 8 right here. And we would have 2 8s in the tree, but we still don't violate our properties. We kind of do the way I worded it, but since we're breaking ties to the right, our property becomes everything less than to the left, everything greater than or equal to the right. So from the node 8, everything to the right is still greater than or equal. So our property is not broken. Just based on our decision for ties. If we insert 10, and then where is 14 goes is a replace 10. So if we do 10, it'll actually go right where we put that 8. 10 less than 5, false. 10 less than 8, false. 10 less than 14, true. It goes right here. And that doesn't break any properties. So if we have 10 right here, 5, everything in the right subtree, including the 10, is greater than. 8, everything to the left, less than. Everything to the right, greater than. 14 and 10. From 14, everything to the left is less than. Everything to the right, which is nothing, is greater than. The 10 has no children. The property holds absolutely if we insert 10. It goes to the left of 14. It doesn't move 14. Spoilers, in 250, it will start moving things. Things will start moving around. For 116, nothing's going to move around. We insert 10 to the left of 14, and the property holds at every single node. It's still a binary search tree. Our algorithm is not broken. Everything works. Yeah, starting after spring break, that's when it's weekly. Okay, so let's insert. The way we're inserting, that property will always hold, especially if we don't insert any ties. We don't have to think of that asterisk, like, well, except for ties. If we don't ever insert a tie, no matter what, using this insert algorithm, it will always, always, always be a BST. Those two properties will always hold because we're basically enforcing the property in our checks. We're using the comparator to ask whether we should go left or right, and that's exactly maintaining the property of a BST. Okay, any questions on insert before we talk about find? Find's very similar, but a little different. Okay, let's do find. So with find, we are going to make an assumption. We are going to assume that the property of a BST does hold. And we're going to look for this value. If it's in there, we return true or false. True if it's in there, false if it's not. So first, if the tree is empty, it's not in there. Tree doesn't hold anything, nothing to look for, easy day, return false. If the tree is not empty, then we're going to start our recursion. And our recursion is set up the same way. Our helper method is going to take the node because we have an extra parameter that we want to take, an extra piece of information that we want to track through our recursion. So we're going to add that node here. You can kind of think of this extra variable in the helper method as whatever variable you would use in your loop. What are you using to loop over? Well, node not equal false? Well, that's your parameter in your helper method. And then the value that you're looking for, every stack frame is going to need to know what it's actually supposed to do. Well, it's looking for this value, so it needs that information as well. So those are our two parameters in this case. If your use case needs more information, add more parameters. Anything you want to pass between stack frames, add it as a parameter. So we're going to start at the root and give it the value that's being inserted. We're going to use our comparator very similar to what we did before, but we're assuming the property holds. And since the only way to get values into this BST is through our insert method, this property should hold. With one caveat, since we take a type parameter, we don't know what type these things are. We don't know what's going on with those, the values that we're storing at all. So if somebody else, somewhere else in our code has a reference to one of those values, they can go to the heap and start changing things out from underneath us and completely mess up our tree. Like, that's always the case. Another reason you should be very careful when you're handling references. If you have a reference to an object that's in this BST, you might break the BST if you change that object. So just being careful about things like that. But if these values do not change, then the property will hold because our insert method enforces the property. So we're going to take advantage of that. We're going to ask our comparator, the value I'm looking for, does it come strictly before the value at this node? Because if it comes strictly before, remember how our comparator works. It's going to return true if the first argument comes strictly before the second argument and false otherwise, including ties. So if that's how it works, we're going to say, is the value I'm looking for strictly to the left of this node's value? And if this returns true, we get into this block where we're going to say, okay, we're thinking left because the value I'm looking for comes before this node's value. So I'm thinking left, I'm going to look left, and if I look left and see nothing, well, this value is not in the tree. Game over, return false. If that node is not null, we're going to recurse and move over to the left through recursion. Put a new frame on the stack with that node, a reference to that node, the left node, move over to the left. If the comparator returns false, we have an extra step to make. This is where we seemingly have a shortcoming in our comparator. If we're only returning true or false, how do we tell if we have a tie? How do we tell if these values are equal, if the order doesn't matter? With the Java comparators, it's positive int, negative int, 0 gives us those three modes, those three different return values, but we only have two different return values. How are we going to get more information? Well, we got one simple trick to do that. We're going to take the parameters. If we say, does this come before this, and it returns false, it's either this comes after this or it's a tie. So to figure out if it's a tie, we're going to swap the arguments. Well, does this come strictly before this? And if it says no again, that means we got ourselves a tie. So we're going to say, okay, is the value I'm looking for strictly before the value at this node? No. Well, is the value of this node does it come strictly before the value I'm looking for? If this returns true, then we're thinking right, because the value at this node comes strictly before the value I'm looking for. That means they're not equal, and we're going to look to the right. If we look to the right and find nothing, return false. If we look to the right and find something, recurse, move over to the right, and continue the search. But if this comparator returned false both times, I said, is the value I'm looking for before this node's value? No. That means this node's value is either greater than or equal to toFind. And if I say, is the value at this node, does it come before toFind, and it says no again, that means the value at this node is toFind is greater than or equal to the value that I'm looking for. Well, if toFind is greater than or equal to this value, and this value is greater than or equal to toFind, there's only one option left. We found what we're looking for, they're equal, and we return true. But they're not actually equal. I misspoke a little there. I didn't mean to do that one. I try to avoid that one. They're not actually equal, but they're equal according to this comparator. So the comparator is saying, if we ever get here, the comparator is telling us that the relative order of these two values is not important. They're equal according to the comparator. Now, the comparator might be comparing strings while ignoring case, for example, like we did on the homework. So these might not be identical strings in that case. Maybe one's all capital and one's all lowercase, but they contain the same letters. So they might not be equivalent strings. If you take these two values and say dot equals, it might return false, but according to the comparator, they're going to be the same. Maybe they have the same Bayesian average, but they're two completely different songs. According to the comparator, they're the same. So they're not actually equal, but the comparator says, I'm fine with these being, their relative order is unimportant. I'm fine with them being treated equivalently. So we're using this comparator that returns Boolean, but still being able to get all three of our output values by swapping the order of the inputs. So that's the only wrinkle. Other than that, it's very similar to insert. We're using our comparator, but we're calling our comparator twice if it returns false the first time. Okay, visually, I want to go through this and find the value 4. So I'm going to ask, does 4 come before 5? True. We're going to move left. Does 4 come before 2? False. So we're going to ask again, but with the arguments reversed. Does 2 come before 4? True. So we're going to move right. We know that there's no equality here. So we're going to move right. Then we're going to say, does 4 come before 4? That's going to return false. So we're going to swap the order of the arguments. Does 4 come before 4? False. Since we got false both times, 4 is not less than 4 and 4 is not less than 4, they must be the same thing. According to this comparator, their relative order is the same. So we can return true. We found what we're looking for, according to this comparator. Might not be exact values. In this case, it is. Let's say our comparator was less than like this, but comparing absolute values, and I had 4 and negative 4, it would still return true and say, we found what we're looking for. Okay, any questions on find? With the crux of it being we're dependent on the structure of a binary search tree, the properties of a binary search tree being true. Any questions? Okay. And now in-order traversal is the one that's most useful to us. If you do an in-order traversal on a binary search tree, you visit the nodes in order every single time. So if we think of our property of a BST, where everything to the left is less than, everything to the right is greater than, well, an in-order traversal says, go mess around in the entire left subtree, then this node, then the entire right subtree. So what an in-order traversal on a BST is doing is visiting everything that's less than or comes before the node's value, then the node's value, then everything that comes after that node's value. And that's recursing through every node in the tree, and the property holds for every node in the tree. That's always going to give you the nodes, the values in order according to that comparator, which is the traversal that you're going to want on the homework. You want a BST that's going to store your songs in an order according to a comparator. And then you want to traverse that tree to get your linked list of songs in order according to that comparator. You should be thinking in order traversal. Do an in-order traversal, it will visit the nodes in sorted order according to that comparator. And this is why we like in-order traversal. There are other use cases for pre-order and post-order, but for BST specifically, in-order traversal really gets us what we want. Oops. I only have one slide on this, but I just wanted to tie it into Monday's lecture. Make it very clear, homework 5 or test 5, think in order traversal. Okay, and that's the bulk of task 5 difficulty, is doing that in order traversal, traversing a binary tree, visiting the nodes in order, and getting all those nodes in that order into a linked list and returning that linked list. That'll be what most of you will spend most of the time on for task 5. It's pretty tricky, getting to be tricky. Not objectively tricky, I don't know, I don't think it's too hard, but it's getting tricky at this stage of 116. It's definitely the trickiest thing that we throw at you up until this point. The homework says to use binary tree node, but we use BST instead, or do we use both? So the homework never says that you have to use a BST, but it's heavily implied that you should be using a BST. I think I do mention BST at one point. But the methods will return the binary tree node. So you're going to have internal to your code, you're going to have a BST to actually get the work done. But when the methods are called, what you're actually returning is the root node of your BST as a binary tree node. And then it's up to you. One of the reasons for that is that you get to decide how to structure your BST and how to actually use it. Some students create their own BSTs. Some use the code like I recommend that we give in lecture, just all the code that we just saw. Take that from the BST class in the examples repo. Just use that. But if you want to build your own inside the playlist class, I'll see insert and in-order traversal method. Actually, in-order traversal you have to write anyway. But I'll see an insert method inside the playlist class. And then it always bugs me when there are bugs in, no pun intended there, but when there are bugs inside that method, I'm like, you could have just stole my code. Like there's one time where I'm giving you the green flag and just say, steal my code. They don't, and then they do it wrong, and then, it's frustrating bugs to solve. Don't do that to yourself. Just take my BST class, or Paul's. I forget who wrote that class. Mine or Paul's, the BST class. Well, if we just write a whole bunch of if statements and never use trees at all, I mean, if it works, I mean, the code is a bunch of if statements. I mean, you're just recreating a BST. I mean, you don't know how big the tree's going to be, so when do you stop writing if statements? It depends on what you mean by that. Like, at some point, you got to stop writing if statements. I have to make a test case with a 1,000,000-node tree if y'all are going to be doing that. Okay. So let's talk about the why. We still haven't talked about why. And the answer is going to be efficiency. We don't talk too much about efficiency in 116, but if we're talking about BSTs and binary trees in general, we really have to talk about efficiency because that's the only reason to use these things. If you don't care about efficiency, you don't use trees at all. Why would you do that to yourself? You would just use an array list and be done with it. So efficiency is the answer. Much more about this in 250. That entire course is about efficiency and choosing the right data structure for the job and doing the runtime analysis and all that. So we'll do a little bit today, but not a ton. To talk about the efficiency, we have to talk about balanced tree. A balanced binary tree is a tree where the left and right, for any node, the left and right subtrees are about the same size. They're not always going to be exactly the same size. It's not always possible, but roughly the same size in its right and left subtrees. The tree that we've been using as an example is a fully balanced binary tree. It is perfectly balanced for every single node. Its left and right subtrees have exactly the same number of descendants in them. So that was fully balanced. But if I add one node, there's no way I can add a node and maintain perfect balance. So I say about as close as we can get to balanced. To perfectly balanced. And if your BST is balanced, we get a lot of runtime advantages here. The height of the tree is going to be O of log n, and insert and find are both going to take log n time. So each time we went one step of the recursion, we did constant amount of work, and that got us down one layer, I forgot what I call them, but one layer in the tree. Got us down one level. Got us down one level in the tree. And if the height of the tree from the root to any leaf node is log n, and each time we do constant amount of work, we move down one layer in the tree, we're going to get down to a leaf node, and we're going to return true, false, or find a place to insert in log n time. So we get log n insert, log n find. The two algorithms that we just saw are both going to be log n algorithms if the tree is balanced. And we can also delete a node in log n. We didn't talk about deleting nodes, and we won't in 116, but we could also delete a node in log n time. Notice that we can't traverse the tree in log n time. Traversing a tree, we have to visit all n nodes. Remember, n is the number of elements in a data structure. We still have to visit every single one of them. There's no way we're ever going to make that any faster. All our traverses are always O of n, or worse if we implement them poorly. And If we have a BST and we insert n elements, it takes log n time to insert. Guess what we have? Another O of log n sorting algorithm. So go us, yay. We need another one of those, right? We already saw merge sort in 115. Hopefully they still cover that, and I'm not lying to you. But we like our n log n sorting algorithms, and we have another one right here. Just call insert on your BST n times, insert all your things, do an in-order traversal. It's going to be an n log n algorithm if your BST is balanced. And this is where we finally get our advantage, one of our advantages here. And the biggest reason to use a BST, because like you would say, well, I'm going to insert all my values into an array list and sort the array list. We already have merge sort, does it in n log n. We're good. So why wouldn't I just do that? Why would I use a BST? Why do I need another way to sort? And the answer is if you have dynamic data. If you have data that's constantly changing, the BST can maintain sorted order on changing data in log n time. And I always think of a leaderboard for this. You have 1 million players or 1 billion players even on your leaderboard, and they're constantly updating their high scores and moving around in position. If you have a BST and somebody changes their position, you remove their node, you insert their node, both of those are log n. You maintain sorted order and had log n update time every time a score changes. If you have an array list, that takes O of n. And if you have a linked list, that takes O of n. O of n just to insert if somebody takes over goes from the bottom of the leaderboard to the top and you have the top in index 0. Well, you insert in index 0 and have to copy everybody down one index in this array list. That's going to be O of n time in the worst case. And linked list takes O of n time just to find out where to insert. So if somebody is new to the game and gets a score right in the middle of your linked list, even if you have a reference to the end with a W linked list and the beginning, you're not going to have a reference to the middle too. That gets kind of silly. You're going to have to navigate O of n nodes to find where to insert, and then inserting is O of 1, but it takes O of n to find where to insert. Binary search tree does not have these limitations. You maintain sorted order in log n. So if you have dynamic data that needs to always be sorted, binary search tree helps us, gives us much efficiency there. And our algorithm only checked a couple of nodes here. When we did find, when we tried to find 4 in this, we checked We checked 3 nodes. When we did this, we had a tree with 7 nodes in it, and we only had to check 3 of them to be able to find where we're looking for, which happens to be log n. If we think of the size of the tree is 2 to the 3 minus 1, so we have 8 minus 1 nodes. Log base 2 of 8 is going to be 3. The math checks out for log of n, but we don't really see the power. Like 3 versus 7, that's almost half of the nodes that we had to search. So how does this scale? And hopefully you remember from math class that logs grow extremely slow. We're going to take advantage of how slowly logarithms grow to be able to get our efficiency here. So let's say instead of a height of 3, we have our height 3, our log n height here, and we change this to 1 million nodes total in our tree. What's the height of this tree going to be if the tree is fully balanced, completely balanced? What's that height going to be? From going to 7 nodes to 1 million nodes, we went from height of 3 to a height of 20. Logarithms are extremely powerful. These are extremely efficient algorithms. If we have 1 million nodes that we have to track, 1 million values, and we have log n algorithms, we're maintaining sorted order in 1 million values in log n time. We're only taking an order of like 20 amount of time. Log n is so powerful. 20 units of time to be able to update this leaderboard very quickly. And even if we jump this up to 1 billion, if we have 1 billion, the height's 30. 1 trillion, the height's 40. Every time you add 3 zeros in base 10, you add plus 10 in base 2 after the logarithm, after the log base 2, is a rule of thumb. It's a little off. This is actually a little bit less than 20, slightly less than 20, 19 point something. And this is how, if you ever played the 20 questions game, That's how, this is one way, this is the base thing. I don't think they use exactly decision trees because sometimes you answer a question wrong. But you can think of like just about anything. And in 20 yes-no questions, it can reach what you were thinking of. That's because it can code up a million different things that you can be thinking of and put it into a giant decision tree, could put it into a giant decision tree and then ask you 20 yes-no questions to be able to get what you're thinking of. Like, that's just how math works. It only takes 20 binary questions to navigate the tree. Million nodes. It has to, like I said, it has to do a little bit extra than that because we don't always know the answer. I always get at least one of the questions wrong, and it's able to correct from that. So it's doing something, it's more advanced than that. But this is the general idea. This is the math behind that. Logarithms are extremely efficient. If the tree is balanced, our tree is not going to be balanced. I was very careful in the way I did everything today to make sure that it was balanced, but that's not going to be the case. We do the same exact thing, and instead of inserting in a very careful order, I insert in this order. If I insert specifically in sorted order, I'm going to get a tree that looks like a linked list. So I insert -3, that's the root. 2, does 2 come before -3? False, go to the right. 4, let's go right to 8. 8, is 8 come before 3? False. 8 come before 2? False, 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 insert. We're always going to insert to the right in this case when we're inserting in sorted order. So our tree is not efficient at all. Our BST really sucks. So this is a problem. Everything's going to turn into O of n, and we might as well have a linked list or an array list at this point because we get none of the benefits of a BST the way we coded it here. We have a very simple insert, very simple find. Well, find's going to be the same no matter what. But we have a very simple insert method, and we don't even have a delete method. So how do we do all these things in log n and maintain the structure of the tree? That's the real trick. How do we maintain the property of a BST and maintain the structure of it being balanced? For this, there's something called self-balancing. I thought I had it on the slide. Self-balancing binary search trees, which will be your red-black trees and your AVL trees. These are topics for CSE 250, so I won't steal their thunder. They'll show you exactly how to do this. And you will fix the structure when you insert. If the tree starts getting out of balance, it'll fix itself. You'll restructure it. So you start rotating the nodes to make it balanced again. And then you can insert and delete both in log n time. There are ways to delete a node and fix up the tree to be able to still maintain balance and the property of a BST. So that and much, much, much more in CSE 250. That's the end of where 116 wants to talk about these things. And can I get some music? Too many technical issues today. My music should be playing. We can't leave until it starts. Oops.